On Monday, November 2nd at 3 p.m., we're going to organize a meeting for the most demanding end users of photonics on the planet. You will find them in the best R&D centers where top-level academics are building amazing optical setups. I'm constantly in touch with many of the world's leading universities, and I get goosebumps when I see the great things that they are doing right now. And it's never too early to ask these brilliant men and women about their Santa Claus Christmas list. But to make that breakthrough in biotech or quantum technologies, you always need the right instruments. Remember the Higgs boson theory? Put together in the 70s, it took until 2012 when the Large Hadron Collider in CERN was able to show the existence of a new particle. At one of the last real-world summits that EPIC organized in Barcelona, we heard from brilliant researchers like Professor John Rarity from Bristol University.
What gets me out of bed in the morning is if in the experiment that I'm doing, or if in the commercial device that I'm building, light behaves like a wave and a particle at the same time in that device. And in all of these quantum communication systems, that's what we're exploiting, is the wave-particle duality.
In our meeting on Monday, November 2nd, I'm looking for participation from top-flight researchers in Cambridge, Oxford, CERN, ICFO, QuTech, the European Space Agency, the Fraunhofer Centers, the National Metrology Center in Germany, CNRS, or the new Infotechnology Center set up in Jena, Germany. So to participate in this meeting of the minds, remember to sign up for the Zoom room or watch the fireworks on YouTube starting at precisely 3 p.m. When we understand the instruments that researchers need tomorrow, we can start designing and building them now. It is time to watch the fireworks. Welcome everyone. I'm really excited about this meeting, Sana, because now we have the users being the academics. And believe me, very often the academics think they know the technology much better than the ones who develop it. So it's going to be a really cool meeting of the minds. I just would like to say, first of all, that I cannot thank you enough for what you're doing for EPIC. I would like to say, many of you already know, 2 weeks ago we became the largest association in the world. We keep getting the support of all the companies, and the only way I can thank you for this is to tell you that all my energies and all the coffee I drink is for the photonic industry and to give the spotlight to the companies in EPIC that deserve it. Thank you very much for this on behalf of the whole EPIC team. Today we are celebrating the end users as high-end researchers, but please keep in mind that we, from now until Christmas, we have already a calendar of fantastic EPIC online meetings. For example, on Wednesday we talk about DCIs, data center interconnects. Next week, write it down, water quality monitoring and purification, and we're also going to address topics like quantum technologies, 3D sensing, medical devices, laser flow automation, even photonics for the food and beverage industry, which will be just before Christmas time. Also would like to say, many of you know them, these are the real stars. I'm just an entertainer. The real stars are working from Monday to Sunday, trying to scout all different end users in all the markets. Thank you so much, the EPIC Dream Team, for organizing these great events, providing network access to the network. Any company that wants to get in touch with any EPIC member, just let us know. We'll make the introduction. For raising capital, if you are looking forward to raising capital for your company, please contact us. We have the right tools for that, and we get no commission, because all we want is to give value to the members. We have also the biggest website in the world to find a job in photonics, www.jobsinphotonics.com. And all of you know this because you're EPIC members. You have a long list of market reports that are free, accessible for you as an EPIC membership benefit. That's all I wanted to say about EPIC. Now I want to talk about high-end research. This meeting would not have been possible without the support of some of the great EPIC members that are supporting the event today. First, QuTech, all the way from Delft, the Netherlands, research on quantum technologies, leading the research of quantum technologies in Europe on many different segments, especially on the quantum computing market. Irisome, the company that we have in EPIC for the lasers for medical and other applications. OptoSigma, if you are looking for component supplier or stage supplier for any kind of photonic manufacturing, go to them, especially optical filters are great. WISTA, any association Association wants to look at the way that WISTA do things, always helping the companies addressing their markets, always helping their cluster, really looking forward to the next stage in development. AMS Technologies from Munich, this company is the one who has made a business of added value distributions. Their people are system engineers, understanding the challenge of the people and being able to provide the right solutions. Asphericon from the capital of optics in Europe, which is Jena, Asphericon has made a paradigm shift on the different typical values that we consider metrology for freeform optics. They make the most accurate freeform and spherical optics in the market. And last but not least, laserpoint. You're looking for a metrology solution for characterizing your laser diode, your high power laser. Laserpoint has the right metrology solutions for you. Thank you very much, all of you, for supporting this event. And we have a great agenda, Sana, a great job today. We have a great agenda with some of the top rock stars today asking us about their Santa Claus Christmas list, the shopping list. We want to understand from these people and also from others in the room, what is your wish list in terms of photonic devices, photonic products. I want to satisfy them together. All of you are going to be able to get in touch with all of them. And also, we are streaming this meeting live in YouTube. So now allow me to say hello to the YouTubers. Hello, YouTubers. How are you? All of you watching the meeting in YouTube, if you want to get in touch with any of the participants today, all you have to do is send me an email, jose.pozo@epic-aso.com, and I will make the introductions. If you have any question during the meeting, please use the chat. This is also valid for the people in the Zoom room. If you want to get in touch with each other, please use the internal chat for that. After the meeting, we will have one-on-one meetings for you to talk privately with the other people that you can do business with. For the instructions, please stay alert on the chat. Helena Jelinkova, hi Helena, is gonna give you the instructions for this. I think that's it. I think it's time to get the ball rolling. Thank you so much for this amazing day that we're about to have. For the next 2 hours, let's understand the shopping list of the end users in the academic sector. And there is, believe me, there is no better way to start this meeting than with our first speaker. Professor Juergen Popp is the reference when it comes to bringing research to the medical market. He's been helping EPIC a lot in the biophotonics segment, and he's one of the leading professors in this sector. Professor Popp, thank you so much for accepting the opportunity of opening this meeting today. The floor and the attention of everyone goes to Leibniz, goes to you.
Sorry, I forgot to unmute myself. So first of all, many thanks for having the chance to give here a quick insight into the technology, what we have been developing over the last, I would say, almost decade. It's a compact multimodal nonlinear imaging platform for biomedical diagnostics. And I'd just like to show you what it is about. So we combine here different optical modalities, coherent anisotropic Raman, probing molecular information to photon fluorescence. We get information on proteins, enzymes, and we can also probe here morphological information by using SHG. And we produce those multimodal images. However, in order to get this to the physician into the histopathology, we correlate this first with histopathology, and then we work quite strongly on a computer-based spectral histopathology so that we can translate this directly, our images, in something what the pathologist can understand. So what is the advantage? We are working here on an automatic prediction of tissue or cells, and this can be correlated with diseases. This you can use in medical field, but also in life science. And you have an instant feedback together with IAR and with the pathologist. And what is the big advantage? We have developed a technology where we can really miniaturize the workload due to optimization. What does it look like? So this is our microscope we have developed. It's highly mobile, it's flexible, this is a multimodal approach. What is quite nice with the development of fiber lasers, we can have this 24 hours, 7 days per week, and the working and it's maintenance free. It's quite fast, and we can scan large areas in a very short period of time. And at the same time, when we produce those multimodal images, we can direct work on the classification, giving feedback. And here, for example, in the field of medical diagnostics, we can distinguish between cancer and non-cancer tissues with high precision. Now you may ask, why do we need to present here something? First of all, yes, we have worked for many, many years in this. We have a lot of intellectual properties on the hardware, but also on the automated image analysis. And this is a nice collaboration, as you can see, from academia, a partner from the academia. So we have here strong cooperation going on in Jena. Nevertheless, what is missing so far? First of all, in order to get this into the hospital, we need more clinical validation, and this there we need finances in order to get these clinical trials going. We need also support with hardware programming, electronics. We would like to go to augmented reality to display the image analysis results directly. And certainly we need also support for the implementation for the European Medical Device Regulation. As you may know, this is quite challenging with these new regulations. We need support by obtaining the CE marketing, as well as we need somehow industrial partner as customizer. And with this, I'd like to thank you for your attention, and I will give back to Jose, please.
Thank you so much for this great talk. And it was really interesting to see your work. And you know, now I have to ask you what we call the epic question. And let me start this way. So we heard a little what you can do for the others, and we want to know what can the others do for you.
So as I said, at the very end, what we need is what we want to make it much faster. And there, for example, we'd like to combine detectors even closer to the working on the signals, yeah, so that we have more or less on the detector directly the signal being produced and even mainly also analyzed. So this might be something which is quite would be unique. So in order to speed up the entire process, I think on the side of the light sources we are quite good. We have a laser partner here from Active Fibers here in Jena, you may know, and but on the detector scheme, on the microscope scheme, it would be great if you can go there towards, let's say, technology which is even faster in order to speed up the process. So at the moment we have a speed, we can scan in 2 minutes, 1 square centimeters. If you can go much faster and scan larger areas, and then going also for in vivo. And this means we need to combine our data analysis also with augmented reality, so that you can directly translate what we have seen detected inside either a screen or even inside the patient, yeah, so that the physician has direct access to the molecular and chemical information. So at the very end, speed.
Professor Popp, this is very, very interesting. And when you saw this slide, I actually got goosebumps. There's so many things that we have to do to bring a new multimodal microscope into a clinic. And there is here a lot of room for cooperation with industry on the marking, on the regulation, on actually maybe even the clinical trials, clinical validation. But it is not clear. There is not a shop where you can buy this. Which companies can help you with this? Do you have an example or a Christmas list of companies that we could introduce you to help you on that?
Not really, because at the very end, we need the entire system being established in such a way that the different components work nicely together. So at the very end, I think we need people coming from system integration and then going down to the components itself. Yeah. So we are not a system integrator. Yeah. So we have built this microscope and we can show the functionality, but in order to get this really towards the market and that the physician or the, let's say, the end user can benefit from this type of technology, we have somehow also to redesign this. So we need also access to have medical end users and medical device producers on board.
Of course, we have here a beautiful list of people who would like to help you on this. But for me, the main challenge here is that we do have a problem in the supply chain when it comes to medical devices, which is that there is a long-term time to market. And there is also the fact that, as I said before, there is not a clear place that can actually enable the manufacturing of these devices. So I'm going to ask a company that actually have put themselves in the medical market quite quickly. The company is Irisome. Thank you very much for joining the meeting today.
Hi, yes, thank you, Jose.
William,
So,
you have experience on this. You have experience on closing the gap. Is there any advice or any potential cooperation that you see with Professor Popp on helping them reach this medical market?
So I guess just to a few words about the company. So as you said, we as in introduction, we are manufacturing a laser device for aesthetic application. So for this application, we will have to get I would say to conform our product to the European regulation. So that's not the case now, but we are working on it. So I would say we are just at the starting, at the beginning of this process. So for the moment, I'm not sure that we are the best partner for this to help Juergen on this task. But sure, we can just discuss together if we can just help us each other and also find a room of cooperation on that. So
we definitely can share best practice here. Another company in Epic, which is also has managed to close the gap and develop product for the medical market, is a company Lisa Laser. I'm a huge fan of this company. Samir, thank you very much for joining today. You have seen the presentation from Juergen. You know exactly what are the challenges to get all these approvals and CE markings. Is there any best practice sharing or perhaps some room for cooperation you can see with Professor Popp?
Yeah, hello everybody, and thank you for your question. From my point of view, I mean, we did in the past many steps like this, from let's say prototyping to a medical device certification, and we do also have a RA and QM department. So we can definitely help Professor Popp, even if it's just let's say information on the classification of the device, because this will give you the direction and also the deepness of the documentation and so on. So we are always happy to collaborate and also to help each other. We do have also some very excellent external partners for some of the documentation work and so on. So from or in general speaking, from Lisa's point of view, we are definitely willing to help and collaborate.
Let me stress once again one of the points of Professor Popp. They are not system engineers. They are very high-end science, right, Juergen? We are looking for partners to help them with the system engineering of this future microscopic system, because to get all these marks, to get all this process through clinical trials, we also need companies who can do the system engineering of that. Is there anybody who would like to comment on this? We have Guy from OptoSigma. Hello, Guy. How are you doing?
Yes, I'm doing fine. Thank you for today's meeting. Very exciting. You know, I have enjoyed for quite a long time. And thank you for the first talk. Is very interesting. I think OptoSigma can help you in integrating your microscope, including mass production and also including regulation in Europe and also in the USA, FDA, and also in Japan, because our manufacturing plant in Japan are already certified for medicals, because we have experience in dentals, in surgery, and also eye surgery systems. So anytime I think we can get closer, and maybe we can discuss closer in the future. And it just all depends the time frame you have and what is the requirement we can discuss.
Okay, great. Then,
even financially, we can participate to your project.
Okay, sounds very interesting. Great, thank you.
OptoSigma is interesting.
Yes.
But also there's a company in the Netherlands called NTS. Frank, are you there?
Yeah, I'm here. Hi, how are you doing?
How can you help my friend Juergen? Because I love when my friends work together.
Yeah, well, I think NTS is very experienced in development, engineering, cost engineering, and assembly of optical devices or modules. So pretty sure we can also help there. We already work a lot for life science companies already. So we don't do the medical certification ourselves, but I already have contacts with a couple of companies that can help with that. So I think I can close the gap.
Great.
Juergen, NTS has actually been closing the gap in consumer market, and they are excellent on the integration of light sources and optics, also for 3D sensing. So this is a company that definitely can play a big role on a future collaboration. Anybody else would like to comment? We have a really, really nice interactive group of people today. If not, Sana, what is next in the agenda?
Oh, I'm so happy this discussion started. Oh, yeah, please.
Juergen.
No, just many thanks, to this nice contributions, and the feedback,
Oh, but Juergen, please stay with us because I'm coming back to you later.
There's still a lot to hear.
I'm not leaving.
Thank you so much again, Juergen, and Jose. You will have a lot of introductions to do later. A lot of work for us. This is really good. So the next speaker is from PTB, and I have a special feeling. That's where I made my PhD, actually. So PTB is a Physikalische Technische Bundesanstalt, and it's the federal agency for metrology in Germany. Amado, how are you doing? Unmute. Unmute, please.
Okay.
Excellent.
Now you can hear me.
Yeah, we can hear you. How are you doing?
Okay. Yeah, I say thanks. Thanks for the invitation. I'm doing very well. I'm happy to be here again.
We are really looking forward to your talk. So please start.
I will share my screen now with you, and then we will start on. Okay. So let me see. I have
so Amado, it's a very nice phenomena that happened this time, that our member Finetech asked Amado to give a presentation. We have our members preparing the speakers with us now. This is really amazing. So yeah, please.
So I hope you can see now my screen, right?
Brilliant.
Okay, so I think I will go very shortly to my slides. So one thing perhaps some of you know is that we have at the moment the nice wave, so to say, of pushing forward research from quantum computing and try to place it into the market. So trying to use some basic research for actually providing solutions to the industry. Well, we are also one of those groups who started very early doing quantum computing research, and we basically work with trapped ions. As you see in the screen, we show ion trap chip, which basically on top of that, we trap beryllium ions, and with the fields which are generated by integrated microwave electrodes, we can actually manipulate the internal state of the qubits. Okay, so I won't go too much into detail of this this time, but rather I will show you, if I can move to the next slide. Let me see, how can I move to the next slide? Okay, next. So basically, as I shortly mentioned, we use integrated microwave to do the manipulation of the qubits. In this picture, as you can see here, we show as a sphere the atom. And basically, we don't use only microwaves to manipulate the internal state of the ions, but we also use laser beams. And one of the current challenges, not only in our group, but worldwide, is how then I can integrate these lasers into the ion trap chip itself. So there are different approaches. Some groups in the USA have already succeeded to integrate some of the wavelengths, some of the relevant wavelengths actually, such that they can manipulate, they can read out the state of also the ions. Yeah. There are some challenges going in this direction, and one of these challenges is that we basically work for most of the ions in the UV range. So these will, for instance, imply, working or developing waveguides which should be in the UV range, right? This is one of the main challenges. And additionally to that, we would like to also integrate other quantum control tools, such as microwave, as we have discussed, also photon detectors or low noise electronics, in order to later on build a demonstrator with up to 100 qubits. So what we basically need is integration, right? And because currently the way we do it at the PTB is using standard chip mounting technologies such as wire bonding or gluing of materials. As you can see in this picture, we have a chip which has been wire bonded to a filter board. And this, in the future, we want to do it using flip chip technology. And this is how we came into contact with the company Finetech, as we require precise alignment, so below 0.5, not right at the moment, but for the future when we try to scale these signals that we apply into the chip to hundreds of DC potentials, for instance. Or also, if we increase the number of contacts here, so we can improve the thermal contact of the chip when the chip can be contacted from the backside, right? For also this mounting technology, we don't require only one specific type of material. So we would like to test different type of materials, and also at using as small as possible dies. In this case, we also plan to be perhaps in the tens of microns, but also we like to have large pieces, so to say, which up to centimeters. So we need a lot of flexibility from our side. And that's why we came to know the company Finetech, as they offer, for instance, among of other equipment, the Fine Laser Sigma. And this Fine Laser Sigma actually provide us solutions to what we actually currently needed, and also provide us solutions for the future. As for instance, we can move out for the arm of 1,000 newtons, for instance, to increase the number of bonding contacts that we will require in the chip. And also provide us different techniques or technologies to do this attachment of the diodes to filter boards, such as thermocompression, addition, or soldering, etc. And as I think that will be from my side. If you have some questions, then you can let me know. And I think also we still have a few minutes for the company to present some of their nice tools, right?
Indeed, Amado, of course. Here is when we have the two sides here. On one hand, we have PTB as the customer, the end user today, and we have the company that made it happen for you. We have Finetech. Thank you very, very, very much, Hermann, for being such a great supporter of EPIC and making my life so fantastic when I see you in an EPIC meeting. What did you do for PTB, and what can you do for companies like PTB? I think we have you muted, which is a pity because you have such a great voice.
I have to change.
Yes.
I have to mute.
It is perfect now. Hermann? Hermann, we can see your slides, but we cannot hear you, which is a pity because we really want to. Yes, loud and clear.
Okay. I'm sorry I missed that. Okay, thank you, Jose. And thank you, Amado. Well, I can explain to you a little bit later what basically we delivered to the PTB. First of all, maybe a few words to our company for those who don't know us yet, actually. We have about 200 employees worldwide, 6 subsidiaries on 3 continents. And actually, we are producing, or we came from the area of tabletop models. That's why most of the universities and research facilities involved in photonics are our customers, including PTB, MIT, and the Fraunhofer Institute, who will present later. And as you can see on this slide, actually, we are focused on prototype to production now. This means when companies develop a new product, they typically have in mind that they want to produce it later on in higher volumes on a production system. So when they start to develop it, the development should be done so that the product later on, or the process later on, can be transferred to a production system without requiring a second development loop. And that's why we introduced the prototype to production already in 2013 as a Productronica. We presented the Femto-1. And now we have taken it to the next level where the modules and tools can be used across the product family. Process recipes, parameters, libraries, everything can be transferred from the tabletop to the production system, and the recipe just needs to be completed rather than newly developed. And this brings us to the real slide, actually. You see on the left side, you can see the Lambda 2, which is a system which is the ideal choice for photonic applications due to the placement accuracy and process flexibility. Next to it is the Sigma, which is a machine which PTB has, which is a kind of super Lambda 2, but it already has a vision system and bond forces up to 1000 Newton, just as Amado already mentioned. Next to it then is the Femto-2, which is an automated system with high placement accuracy and utmost flexibility for R&D and small to medium-sized production volumes. And last but not least, actually, we have the Femto-Blue, which is a simplified femto with placement accuracy of 2 micrometer. Yeah, if you would like to learn more about our systems or want to have a free demo, which is of interest, of course, for all the researchers here, which can be here at our company once the lockdown is lifted, or can be online, or you can visit us at www.finetech.de. So if you have any question, if you need some assistance in developing your product, just like what we did with the PTB, actually you can contact us, we can produce you some samples, we can work with you on the process and try to make your new product work on a lab bonder as well as on a production system.
Thank you very much, Hermann, and thank you very much, Amado, for this. For all of us, especially the one who did a PhD in quantum physics and in semiconductor lasers, we spend so much time aligning fiber to the chip. And I just love when automation companies like Finetech are accelerating by a factor of 10 the development of experiments in the laboratory, and that's really fantastic. I'm gonna go first to Amado. The reason I'm gonna go first to Amado is because the days are very long. This morning at 8 o'clock in the morning I was giving a presentation. and I showed them this slide. I showed them this slide because we were talking about quantum clocks, which are maybe my passion, maybe some of you know this already, and the idea of the need for photonic integration to integrate all these amazing optical benches. When I go to PTB, I'm sure I will be amazed by your beautiful set of OptoSigma optics everywhere. Are you looking for cooperation with photonic integrated circuit companies, Amado?
Yes, well, we don't work yet directly with one of those companies, but of course will be very interesting to hear perhaps the opportunity to have some solutions provided by the industry partners. As you show very nice, this big picture is kind of what we want to avoid, right? We want to move out from that, and we want to have actually as compact as possible, well, the so to say lab on a chip solution for photonics, yes.
So I think you're gonna be quite surprised. I have lots of pictures like that one that I show you, like a lot of them, because they are example. I want to ask the big foundries in the room. First, I'm gonna go to Lyonix in Enschede,
Yes,
the Netherlands. Paul, when you see a setup like that with so many different optics and they say that it's a quantum clock, and you just see a Metrology table that is 5 by 5 meters, what is the first thing that you think?
Well, the first thing is, what do you think is that we kind of made the similar transition over the last 15 years integration of chips on one platform, migrating lasers on the chip level and bring them together, indium phosphide chips and triplex chips. Actually, what we call our hybrid platform. So we have made a transition. What makes me very happy is also if I look to this application that requires not only the telecom wavelength as we know it, the 1550, but also UV or visible light as I have in the backside of my screen, because our platform is typically used for visible light and for telecom wavelengths, because we use silicon nitride as waveguides. So this kind of matches and fits with our platform, and we are very happy to learn more about the application and see whether we can be a partner in this.
Earlier last month, there was a company in Spain called QSight that actually put a photonic integrated circuit-based product in the market. It looks crazy. It looks like 10 years before we were expecting this, but they actually made a product, a quantum random number generator in the market using photonic integrated circuits. And that really shows that we are there yet. But when it comes to these quantum applications, Amado, every photon counts, right?
Yes, of course. Yeah, this is very important to have high quantum efficiency. Depends, of course, on the type of interaction we want to get. If it's just to collect some light, which is not related to the fidelity, of course, is not so important. But for high fidelity, yes, it's very important.
There are many companies in photonic integration that really saw an opportunity to help the quantum companies. So you also have heard the company PsiQuantum from Bristol as well, that now is based in California, developing quantum computing-based photonic integrated circuits. There are many examples of this. One person, Michael from Leibniz, has actually been helping many R&D lines in quantum technologies to incorporate photonic integrated circuits. Michael, how are you today? From Switzerland.
Good.
When you saw the presentation from Amado and we saw these beautiful pictures about all these optical benches with all these optics, does it ring a bell? Is there some potential cooperation here?
Well, of course, it's the picture that you showed before, and also what Paul from Leibniz stated is that taking the key building blocks, it's probably a stepwise approach. No, you don't make the jump from this whole lab into one single chip, but it's a stepwise approach where you take building blocks that are very stable in photonic integration and put them into photonic integrated circuits. And then, as an addition, I think what we really have to look here is where does photonic integration gives an additional plus. For example, with the nitride, with the thick film silicon nitride we are offering, you can also address the nonlinearities of the nitride at very low loss. So you can generate a frequency comb or supercontinuum that helps you, for example, to stabilize the atom transitions that you're looking at. So that's another tiny building block that can replace a lot of optics in that system.
Amado, a couple of months ago, a company, Epic member, CSA Catapult in the UK, put together a beautiful slide. I can share with all of you later if you're interested about what are really the challenges of quantum technologies that can be addressed by photonics on different application fields. And when it comes to sensing, especially in harsh environments, a co-packaging of silicon photonics and compound semiconductors, light sources, are really a unique need for the supply chain. Do you share that view? Is there a need of more complex photonic integration that can actually enable the quantum atomic clocks that you have in mind?
I cannot unfortunately speak for the whole community, but for our application, the main requirement, the main challenge is to get integrated photonics in the UV range. That is a very, very needed challenge. So I'm talking about the wavelengths of in the 300 nanometers, so a little bit below, so which is the big need, so to say, from our application.
I think at the end of the day, it's all about packaging, but that's why you had a great partner in Finetech helping you with a part of packaging. I have many laser manufacturers in the room who are wondering, when are we going to talk about lasers? Give us the Santa Claus Christmas list. What is this wavelength that you are looking forward to have eventually, or this power or this repetition rate?
Well, power is actually not so like the requirement. We need actually a few microwatts to address, well, directly on the qubit itself. But of course, we want low losses. We don't want to heat up the chip. And as I mentioned, one desired wavelength, which is one of the long-term goals for us, will be 313 nanometers. And yeah, like this, there are other types of species, like 397, for instance, for calcium, and then some other wavelengths. But mainly these two wavelengths we are looking for.
He's looking for a three. Can you repeat the names? 313 nanometers and?
Yes, 313 and 397.
Anybody would like to comment on this, or perhaps find a room for cooperation? If not, of course, I will put it in the summary slide. And when it comes to the light source, then it's also the counterpart, the detectors. Detectors are this unmet need, this huge unmet need that everybody wants, that it operates with the highest quantum efficiency and cooled and small, and it can be packaged easily. But realistically, do you have some demands for the supply chain on the detectors?
Well, this will be also in the similar way, well, actually the same wavelengths, because these are the wavelengths where we read out the state. And well, efficiency, that should be, I think, like, I think the standards are around 30%, I think, at the moment. I don't remember exactly. But yeah, and there are some challenges with that regarding cryonic environments. As also we want to place these photon detectors into cryonic, but some of the research groups have come up with some solutions in the USA too.
Fantastic. Hermann, when you work with companies like PTV, who I keep saying these are the most demanding end users that you can come up with, because every photon counts for them and they have very high accuracy. You don't care how repetitive it is, but they really want to have things work as soon as possible. What are really the main challenges on working with an institute like PTV, which I'm sure is a fantastic customer? What are the key challenges here to share best practice with the rest of the community?
Well, I think actually one of the major challenges, besides that they require, as Amado already said, that in the future they will be needing a much higher placement accuracy. You need a very high bond force actually for it, because you have many bumps in the end if you go for flip chip actually. So you have to apply the force, you have to apply heat, and you must be able to do that without wasting lots of material. Keeping in mind that, okay, atomic clocks will probably not be exactly a super high volume product in the future. However, as I said, if you're producing only a few of them, you cannot waste too much material. So it comes down to that you're knowing your process, that you're knowing your bonding results, your parameters, everything what you need. So basically, it's a whole package of process parameters, process experience, and machine capability.
Thank you so much. Thank you so much, Ermeneux. This is really nice.
But why don't we do something, Sana? Because I really still think that we have to touch a bit the quantum part. I'm gonna go to New York. I'm gonna go to PLX. Martin Rost. We have here Amado telling us about their metrology systems and their atomic clocks. I know that's a particular segment, and PLX has taken very seriously and developed technology for key companies in this sector. Is there any potential room for cooperation between PTV and PLX?
It's definitely a possibility. We're currently working with the United States Naval Observatory on some items that they need for their atomic clock, where they're working on controlling the interaction between light and their atomic beam, and they need the light beams, laser beams, to be accurately aligned, spaced, and that's what we're supplying to them. I don't know if this is, in the same realm that Amado is working.
Amado, whenever you're looking for a partner to make an optical instrument based on the optics that you have, to have it suitable for a space observation, for space applications, for space timing applications, PLX is the right company to have in their network. Thank you very much, Amado. Thank you, Martin. Thank you, everyone. I think it's time to continue with this fantastic program. I mentioned the laser community before. Now it is your time to act. I know many of you are waiting for this next presentation. We have Eli in the room. Finally, after trying from many different corners, Federico Canova accepted to be put on the spot here to asking about their Santa Claus Christmas list on laser-based manufacturing processes. Thank you very much, Federico, for this. We want to know what Eli wants. The floor and the attention of everyone in the laser community now more than ever goes to you.
Thank you, Jose. Let me start the presentation. So first of all, I would like to thank really EPIC for this opportunity to present Eli. Eli, I really want to give you a quick insight of what the project is and where are we now and what we need to go to the next step. So where Eli is coming from? Eli comes from the realization of the European community that Europe is a leader of the ultra-fast activities. As you can see here, you see in the bottom of the slide the cumulated petawatt power available in the lab in Europe, in Asia, and in the United States. And you realize that even before Eli, we had 5 times more peak power than the other community. So thanks to the S3 roadmap, the decision was taken to continue to go further into this leadership. And the Eli project was put together by a grassroots work, thanks to the laser lab community, all the lab that worked individually on lasers and decided to work together. And at the end of the day, Eli facility means that we are adding 5 lasers of petawatt class and 3 lasers of 10 petawatt class to the European portfolio. So what science you can do at Eli? So at Eli, clearly we can develop lasers. We have to develop lasers. We are really working with the state-of-the-art facilities. So we need to have our own development, even if we are buying a lot from the community. Then in terms of secondary source of application, you have all the radiation physics and electron acceleration. We can go from soft to hard X-rays, GeV electrons, to do any kind of experiment or application that you can think about. Then we have heavy ion acceleration up to 250 MeV ions. We have all the application for material science and biology. So all the pumping probe and the possibility to scan the matter down to the smallest and to the finest details. We can go to the very small and to the very big. So with the astrophysics, the plasma physics, where you simulate in your lab what's happening on the sun, for example, or in very distant stars. And then you have all the dream physics for the next generation of theoretical physicists, where you go to the QED, where you try to create, for example, what we call breaking the vacuum. You have complete vacuum, you focus the laser, and then you have matter and antimatter appearing thanks to quantum effect. So this is all the exciting science that we want to do, putting together this project. So to be more practical, what is Eli? Eli is a key partner for innovation. You can see here the picture of the 3 sites. Each one is in a different country: Czech Republic, Hungary, and Romania. And during the construction phase, more than 450 million euro were spent in contracts over more than 19 European countries. So why I say that Eli is a key partner for innovation? Eli is already a success story of industrial partnership. All the R&D equipment that was purchased from companies was delivered in time and at specification. This is a quite new approach for such a facility. Usually the facility are built by other labs. Here we really focused on the community. We trusted the community, say industry can build the lasers, and the industry delivered. So we're very happy about that. Eli is a showcase for your R&D. I can tell you the story of a company that designed a multi-million euro laser for Eli, and almost immediately in the same year they had already 3 other orders for the same lasers. And Eli is a driver for the new technological development. You have to realize that 10 petawatt laser means that each pulse has 300 joule compressed in 30 femtosecond, and these laser shots at a little more than 1 shot per minute. So what are we searching for? ELI needs to operate with a very high quality, to perform a very effective risk management, and also has to think about sustainability. Sustainability means that the long-term costs have to be controlled. So ELI is searching for partners, and we probably spend more than that, but at least there will be 30 million euro per year spent in technology for the operation of the facility. You have to consider that the overall cost of the project was about 1 billion euro. So this, in terms of running costs, we're between 5 and 10% in terms of high tech. We have to develop and characterize high performance optics, crystals, diodes. We have to implement efficiently control command, automatization, vacuum. We have also managed large amount of data. Every experiment creates teras of data that have to be stocked somewhere, transferred to the user, manipulate, visualized. And then at the end, we have also to perform training. This is something that is not really considered usually. We are a community that sell solid, good things, but the training and the capability of the user to highly perform using very sophisticated machine, it's a complete new challenge that we think will make the difference for a facility like ELI. So yeah, I want to conclude saying that ELI, with his structure that will be called ELI-ERIC, has as one of his core mission to collaborate with industry. Thank you very much for this minutes of presentation, and thank you, Jose and Sana, and I'm open to questions.
Thank you so much. This was perfect, and that's very much what we wanted to hear from ELI. Very successful, very fine institution, and it's nice to know you how open you are to collaboration. I think Jose agree with me when I say that this is the right place to be. Here you have very much a lot of people who wish they will raise hand and tell you that they will collaborate with you. Otherwise, I will just start digging in the list of our guests here. We have, let me start with Optica. We have a presenter from Optica. We have, hi.
Hi.
How are you?
I'm fine, thank you. Thank you for giving me the opportunity to be here. This is really great.
I would like to ask you kindly to make the mic closer to your mouth and hear you louder.
Okay, is that better?
Can you tell us what do you think about the talk you just heard now?
Very interesting, yeah. Well, high power is not really exactly our field, but it's very interesting to see where the future is going to, definitely.
May I add that the high power source is something that was now delivered and installed, but in reality, when you have such a high peak power system, you have thousands of diagnostic that goes for more classical lasers. So everything that goes from the fiber laser to the metrology, power meter, everything, temporal characterization. I see that there are people from APE that are very familiar with the characterization of ultra short pulses. So I think that it's really worth it, and we really want to be to have the widest access as possible to the community, because these machines are the flagship, but around this machine there are hundreds and hundreds of systems for diagnostic, for alignment, that goes more to let's say standard and industrial product, are built with industrial parts and bricks.
We have for laser beam diagnostic, we have laserpoint here. Hi.
Yeah.
Hi. Okay. You have to unmute. All right. All right. It's okay. So let me see if we have any questions in the room first before we carry on.
I really love this slide. I really cannot thank you enough for this. Could you tell us, because we have a lot of companies who can help you with the characterization of the optics. This is something that many people in the room would like to help you with. Could you tell us what kind of testing are you looking for?
So you have to consider that for such lasers, we need, for example, mirrors that are 30 to 40 centimeters. We need them to be reflective most of them around the 800 nanometers over a bandwidth of, let's say, 150 to 200 nanometers. So basically from, let's say, 700 to 900 nanometer flat reflectivity to be able to propagate ultra-fast pulses. So we need coating that will be high reflective with high damage threshold, substrates that are extremely flat. In terms of characterization, we need to be able to build interferometric table, interferometric bench. We need to put together zygo-like characterization to measure the flatness of the optics. So when everything is so big, you cannot usually work with the full aperture. So you do by you stitch different parts of your optics, measuring each part and then reconstructing the overall characteristic. There are different approaches. The idea is really we need people that not only provide the instrument, but also the software and the capability to analyze data, to treat them, and to interface them with our control command system. Because otherwise it becomes too complicated to have hundreds of tools, everyone working with his own specific software. You have to learn, you have to tweak it. So we really need integration, because at the end of the day, this facility will be open to user. User means that people arrive with the sample, they do the experiments, they live with the data, but it's really like a service. The user is a customer, is not a scientist that will build his own experiment. So everything has to be perfectly running and with low, if any, problem. So everything has to be integrated.
Uptime constantly. I mean, the problem is that the technicians change every 24 hours with different. I know the challenge. This is a real challenge of every academic or R&D environment, and this is something that I'm really excited of helping about. Because you said something. You said metrology, testing, and on the other hand, you also said coatings. And it will be difficult to find a partner who does both. Could you specify one challenge on the coating side?
The challenge on
what
the
kind of coatings that you think you cannot get today?
The high damage threshold, in the sense that you can have quite often coating that can reflect 200 nanometers around 800, because these are very now well known by the manufacturer. But when you start to have optics that are 300 millimeters, 400 millimeters, you need also to guarantee the damage threshold, in the sense that if you don't want to have beams that goes to 1 meter, you need to be able to have a certain density of energy to transport them. So we need really to have high damage threshold, and especially that can withstand laser in vacuum, because vacuum property of the coating are different than in air. So
many companies last year invested heavily on IBS processes. So IBS coatings are there for you to take. And you mentioned the magic word, you're looking for partners. I'm going to make a lot of introductions. The femtosecond laser community has been booming in the last 2 years in Europe. What challenges or what opportunities for collaboration do you have with companies like Fluence, for example, that make femtosecond lasers?
I think the collaboration can be on a specific topic. For example, if Fluence want to develop something that is not particularly easy to develop. Wait,
Sana just told me in a chat that they are here. I didn't know. Darius is here from Fluence. Darius, how are you doing?
I'm very well, thank you, Jose. How are you?
I'm doing okay. I think you should listen carefully. He's giving you a job. Federico, can you repeat? Sorry.
No, I know that, for example, we are developing also lasers. We bought lasers because we need to operate them and to run them. But we are still developing new kind of source based on ytterbium to have a different, to go to the ultra short pulses with different approach, less standard. So every company that has capability to work with short pulses, with ytterbium, with in general, let's say exotic wavelength. We are searching for 3 micron, 4 micron lasers, because there are a lot of very interesting physics you can do with different wavelength. The workhorse are the classical TISAF laser, because you needed to have something that you could deliver quickly, relatively quickly. But we're working on other kind of sources at different repetition rate, different wavelength, with different approaches, more integrated, like the fiber laser or the ytterbium laser. So everyone that is interested in do some co-development, I mean, we can start the discussion and see if
many people are interested. I'm going to go first to Paris, then to Hanover, and then to Aachen. Let's go first to Paris. AeroDIODE, Sebastien, room for cooperation, opportunities here for you.
Yes, thank you, Jose. Thank you, Jose. I'm going to share my screen. Can you see it now?
Not yet, but I can see you smiling and looking great. But the slide's not there yet.
One thing, yes. Here it is.
Yes.
You can see my screen? Yes? Okay.
Yes. Yes.
Okay, so let's talk about AeroDIODE. So we are in Bordeaux. We are not in Paris, but in Bordeaux. But anyway, we are in France. We are in France. You are right. Thank you, Jose. Just to tell you about AeroDIODE, I'm very pleased to talk about AeroDIODE to many people here, but especially to ELI. We've been created in January 2020. We are a spin-off from Alphanov, so we are located in Bordeaux. We do offer many optoelectronics products. We talked about ytterbium right a few minutes ago. Most of our customers work with ytterbium, of course. We are already on the market for photonic systems. So the technology we offer is mostly around electronics, optoelectronics for laser diode drivers, like ultra low noise laser diode drivers here. We also have some very fast, ultra fast, high speed solution for like AWG, arbitrary waveform generator based solution for driving laser diodes. We also have some solution for signal synchronization, and we work a lot with SOA. Just for, SOA can be used for amplification, like semiconductor optical amplifiers, but it can also be used for as a fiber intensity modulator, and it's very efficient and it can meet very nice performance at various wavelengths. So we talked a few minutes ago. We talked about this, this big R&D setup with a lot of equipment, which are very, very, with only a few room in the room. I want to show this picture on here about our solutions. We help R&D teams removing their, their like 19-inch rack, big racks. If you take our equipment, you can have a very small form factor here, and you can just drive them with a single computer very easily. So you can have like 10 equipment like that and drive it very easily. So it can help going faster. Some customers said that before they use several hours just to start an experiment. They arrive at 9 in the morning and they start the experiment at 11. And they say that just with this type of driver, they can just take 10 minutes and then they drive the experiment. So it helps our customers save a lot of time.
Thank you very much for this. There will be also a lot of room for comparison, a lot of opportunities here. I'm going to go quickly now to Hanover, Laser Centrum Hanover, because Lars has something on his mind. Lars.
Yes, thank you. Thank you for your presentation, Federico. I just wanted to sum up and follow up if I understood you correctly. So you're looking for large optics with high bandwidth for femtosecond lasers and operation in vacuum and high damage threshold. There's a lot of companies out there that can do excellent coatings and can do large optics. Can you help me understand a little better what exactly is the bottleneck, the combination of it all, or are there already companies that can do excellent small optics and do the scaling for you in size? What is the exact challenge in 2020?
We were thinking like you when we started to buy the optics, and then we realized that excellence was not exactly enough for what we needed. Actually, there are many optics that can be, many companies that can produce optics, but we haven't found anyone yet that could make all the parameters on the same optics. Mm-hmm. There's a lot of dispersion from batch to batch, and we consider that a simple relationship between supplier and customer is not enough. We need to do some co-development. So we are searching for partner that we are ready to put some money on the table, but we need someone that that want to do a certain path with us, because we think that our needs are really specific. But you have to consider that all these you have seen these 400 petawatt that are in Europe, then the US and Asia. All these lasers will use these optics. So we think that ELI can drive and open the way. There will be some money necessary to do the R&D, but then there will be a certain market. We're not speaking about hundreds, but probably tens of optics each year of this kind. So that's why we search for a partner. We think it can be a business model that can work, and but it will be a 5-10 year program, and we really need to work with someone that want to get committed for such a long time. And usually companies are on shorter, obviously for other reasons, on shorter return on investment.
Federico, together we are going to drive now from Hanover to Aachen. Tobias Muller has also something on his mind. Tobias.
Yes, Jose, thanks a lot for giving me the word. So thank you also very much, Federico, for this very nice presentation. It's indeed fantastic what you're doing. And you've been mentioning that you have a lot of different types of lasers, and especially with the multiple wavelengths. So I assume you have beam frequency conversion inside these lasers. Are you building them yourself? Do you have custom instrumentation for it? Or how are you making these kinds of lasers?
So we decided to buy all the lasers that we have. So different manufacturer. Most of all the high peak power system are based on TISAFT, pumped either by neodymium YAG flash lamp pumped laser, either by diode lasers. Then with let's say more the different wavelength are based on OPCPA system that are pumped with more classical ytterbium pump, and then with this OPCPA crystal you can play with the wavelength. You can really tweak. Our supplier, our company like Thales, Amplitude, Light Conversion, Fast Light. So company that have very different capabilities. Now we are really trying to go for more classical system that are on the market from not every system, because we need to do some pump probe, alignment, diagnostic, even to do some different configuration for the experiment. So that's why we are searching also for a set of complete commercial solution, maybe with some small customization.
Okay. Yeah, I was asking, as we have a new machine in our portfolio just currently being set up that has 3 collaborative hexapods, and you can build resonators with it in our open access environment, development environment. So I think I should talk to your suppliers.
But also we are also a part of the activities that are on. We are building a gamma source in Romania, where we're using a large resonator, where we amplify the electron energy, basically running the electron in the resonator and adding photons, and the photons transfer the energy during the resonation. So definitely there can be resonator are something that we are very interested in. Okay, perfect.
Thanks a lot. So I'll reach out.
Definitely.
And Jose, you asked me to share my screen because
this thing that you just said is something they want everybody to see. So please share.
Yeah, by coincidence, I have prepared one slide. And so I'm cheating a little bit, Jose. It's 4 slides in one, but so I have to give a quick introduction to what we're doing and how we can help.
Ultra-fast photonics, faster than the femtosecond lasers that we have. You can share your screen at the bottom. You have the green button that says share screen.
Oh, I'm not sharing yet. Okay,
not yet. We are all super curious.
Oh, come on.
And after this, we're going to have the police from the Netherlands. Goedemiddag. I can't wait for that.
Okay, I got it.
Yes.
full screen. Can you see this?
It's coming. It's here. Yes. Tell us.
Perfect. Okay. So yeah.
You're sharing the wrong screen. You have to give us the other one. So you can go to Anseheistelunginen, and there, with my beautiful German, you can switch.
Now it's better.
No, you're sharing the wrong screen.
Oh, okay.
So you go to the button in the middle there. There you go. Perfect.
Okay. Sorry for the quick hiccups. Yeah. So quick few words to Exemtech. We are a company located in the very west of Germany. We are founded 4 years ago, spin-off from Fraunhofer IPT, and we are now 26 people, doubling in size every year since 4 years since we've been founded, and have an installation base of our machines of 20. And if I talk about our machines, on the top right side, you see our typical R&D configuration of the machine. And we use it to basically accelerate our customers from their lab basically to their mass production. And it's used for assembly, for test, and we also use it ourselves to do services. So we help our customers with prototyping, with small series manufacturing, but at the end of the day, when they're ready, they can get a machine. And it's also installed at many research facilities. I think the specialty to which I want to hint here is our open access software framework, which we will also present in one of the following EPIC events on new products. And that's kind of the novelty of this assembly machine. We provide a development framework that will allow our customers to use it self-sustained and enhance it with third-party sensors to develop their processes to make new products. And I think that's quite the novelty. Down here, I made a list of some of our customers and what we use the machine for. So we use it to assemble micro-optics, PICs and fiber, LiDAR systems, imaging systems, lasers, and quantum. And so I think the quantum photonic application, our customer source or customer reference is QANT from the Trumpf company, and they use it really to use all the root access functions and basically develop new products on it. So if you want to have a live demo, we can make that happen for you. I'll be happy to do that.
Thank you so much, Tobias. It's really nice to have you here today. And thank you so much for the nice talk, Federico. I'm sure we will see you in the future meeting as well. All right, so I'm very curious to hear the talk from Joost today from the Dutch police. Precisely, he's a researcher for forensic evidence. Is that the correct term for it? And he made it clear. Joost, can you unmute? Excellent. How are you doing?
Yes, I'm doing fine.
Excellent.
Can you see what I'm sharing right now?
You can start the sharing. So Joost made it clear we will not discuss any open case and we will not see crime scenes.
No crime scenes at all.
All right. So I'm afraid you're sharing the wrong screen. Can you just change to the other screen?
Sorry, hiccup on this side as well.
No worries. So we just need you to push the presentation mode.
Yes, I know, but I'm sharing the wrong screen.
Okay, you can restart the sharing. So Joost, we met in Photonics West, and you said you're looking for photonic solutions for the police. No, I think you can. You are again sharing the wrong screen, I'm afraid.
That's strange.
It's Hermann on Wieselen in the previous screen. So when you share, just click on Hermann on Wieselen, and then you will be switching the screens.
Then I'll
start again. Just like we did it in the trial version, and that's.
Now, all right?
Yes, yeah. Next to tips, you have Hermann on Wieselen.
Yeah,
next to tips.
Yeah, all right.
Yeah, exactly.
Oh, this.
Excellent.
Now it's good?
Now it's good. You can start.
Now it's good. Okay, very good. I'm very pleased to have the to be able to speak at this meeting right now. So many thanks for the invitation from my side. Well, first of all, I'm very interested to hear all your speaks, but I'm gonna be very practical from my side. Within 14 years of experience in my line of work, I was not that able to go into that much detail as my predecessors just shown us. So I'm gonna make it quite practical. And I'm gonna bring you my wish list, but there are many more I can tell you for what I hope for what the future will bring us for our practical forensic investigation. But yeah, I brought three categories, 4 problems: 3D modeling of shoe prints and tool marks, visualization of gunshot residue. I'm going to be more specific on that, on those cases. And the last, if there is enough time left, the detection of specific metals when surrounded by metal. So there are quite some difficulties there. But all in these problems I'm facing, or we are facing, all the technology has got to be portable, light, easy to use, and well, small, but also validated. So all the techniques got to be very accurate in the results. So there cannot be, well, the false positives must be low. Let's say it like this. First, and I think this is quite familiar for everybody, shoe prints. We would like to digitalize these shoe prints, and these are 3D characteristics. So we wish to 3D model this all. The most famous of all, I think, is bottom left or bottom right. It's a shoe print left in sand, which we nowadays photograph or use cast to make a sample. In the middle, we see a dust print left on the floor. A burglar walked over the hard surface of the floor, and we can use a gelatin foil to sample the dust and collect the profile. And most on the left, there is a shoe print left on a tarmac, a roof. All these kinds of different shoe prints, we wish to 3D model, use a comparison modeling tool to compare these shoe prints and combine these with with the perpetrator apprehended. And the accuracy we wish to reach is 0.1 millimeters. So that's not even close to what the accuracies just have been mentioned before. But where photonics comes in is that photonics is non-contact. So all the evidence we wish to collect is as original as possible. So that's what we would like. The collection of tool marks is somewhat similar, but there's only one difference, and that's the accuracy. It's more accurate, and the origin of it is a bit different. A burglar tries to open a door or a window and leaves some marks, and by doing so, we collect during the crime scene a detailed trace, and this is what we see now popping up in the screen. It can vary in width and in height and in depth, but as we apprehend a perpetrator, he hopefully has a tool with him, a crowbar or a screwdriver, and from that we can comparison a reference or a duplicate on a microscope. But this whole process is very intensive in hours, and it's very hard to do. So again, for this part, we wish to digitalize it and to make a database so machine learning can compare it. And this is we have started a project on this part, but we always are open for new insights. The gunshot residue part, we face two problems in this subject, and that's who has fired the shot or held the gun at that moment. And now we see a gunshot cloud around it, around the hand of the perpetrator, and we collect these parts with with a sampling way by using samples, going over the hand. The problem we face on this part is that we do our investigation and close the box in which these samples are brought in, but after finishing, we cannot identify the presence of the gunshot residue on his hands. The second problem is the shooting distance. There are theories like these that we can deduce a shooting distance, but by using a visualization technique, we can make this possible. But the biggest challenge on this part is that these traces are very small. This picture shows a 10 micrometer gunshot residue particle. And some of these are also present from nature. So there is a large chance these particles are just present and just don't say anything about the weapon what has been shot or fired. And the fourth problem we face is, I think we all know this problem where a dog has swallowed the keys, but the same technique has been used by law enforcement to try and find contraband which has been hidden by criminals. These criminals are always trying to transport money or large amounts of money or weapons or drugs in cars and go across the borders, and we don't even find these contraband, but we wish to, and we try all kinds of techniques to find it. But we're hoping to distinguish specific metals. For instance, some materials are not used because they are too heavy. So maybe there is a possibility for us to detect these kind of metals which shield these kind of Röntgen array in the cars. So these are a couple of problems we face, and I'm hoping for some tips from your side. That's all I've got to say right now. So thank you for listening, and I'm hoping for an interesting conversation next.
Thank you so much. This was an amazing wish list, just like we hoped for. You're doing a great job. Thank you for all the service you do. And I'm now so eager to hear and see rising hands to, I see NTS. Frank?
Yeah, I think in some of the topics we already have experience, 3D imaging. So I think, I already reached out, but I think, we can really help. There's a personal reason also, because of course I really want to know what is the NTS or the Dutch police, of course, capable of. That's never bad to know.
This is only the surface.
No, but I really think we have some competences that can help.
Very good. Nice to hear. Thank you.
Excellent. So when you say I want it transportable, so there's conditions on the size and the weight to be handled by the police, right?
Yeah.
So this is to be taken into account as well.
Yes.
I would like to hear from,
That's I think on the gunshot residues, there are also solutions around. based on optical spectroscopy, on Raman spectroscopy. So there are already companies in place, especially in the US. So I can give you some information about the people working there. So I can send you some information, yeah?
Yes, very good. I'm open for it. Yeah, please.
This is very nice. And for the introductions, you also can shoot a short email to me or to Jose. He will write these introductions to easy communicate and connect you to each other. Now I would like to introduce from Heidelberg Instruments. Hello? Please unmute.
Hello, yes, I'm Dominique Collet from Heidelberg Instruments. Sorry I couldn't join on time, so now I'm just trying to catch up with the meeting. And I have nothing to propose for the Dutch police, but I will try to propose some solution to the other people who will talk.
Thank you so much. Let me see if we have other questions in the room.
So MIT here.
Yeah.
This is Kevin Fay from MIT. So Lincoln Lab has technology. If I can just grab your screen here real quick. And here's we've got some standoff detection of trace explosive by photo-induced acoustic signature. This is technology that's already been developed by Lincoln Lab. That's one. The second one is also some technology developed by Lincoln Lab. And let's see here. Actually, I lost it, but I will find it. It's for standoff detection. That can detect that you think about people walking around in a room and they want to detect some type of object on that person. They're able to do that from a distance. So I'd be willing to talk to you later afterwards, and we can talk about further about these technologies.
Yeah, very good. Sounds good.
And we will actually hear a talk also from MIT later. So if I don't see Amado, did you raise hand?
Federico has his hand up. Federico and also.
Okay.
Yeah. Go ahead.
I want to comment about your need in terms of X-rays. Actually, there's some project to have the capability to do X-rays of container. So basically, the size of the source will be a large truck, and it will be able to scan a container and see what is contained and exactly what's inside without opening it. The plan is to deploy this kind of technique at Arbor or at the airport. So this is something that is currently being developed in terms of source. Then when the source will be characterized, we'll need an integrator, an industrial integrator that will put that in the truck. But this kind of sample can be characterized, and it will be useful to have you as user to see exactly what you need. And we can really fine tune your need in the lab, and then you will be a user of the final machine.
Yeah. Thank you for your tip. The container-like, the truck-like, we have that we have that already. Only it is one truck, and this one truck is also is very busy from the harbors and well, scanning all the trucks. So there is not a very large amount of how should I say coverage from that one single truck. So I would see it very small.
Yeah, the point is that the actual truck works with a more standard technology that is based on X-ray generated by tube. With laser, you can have more compact, and as everything in photonics, it will be compact and less expensive because you generate the X-ray just at the end. The rest is just a fiber laser, like many of the one that you can see. So the size of the truck will be mainly because you need a lot of electricity and power supply, but the cost should be reduced, and also the flexibility of the machine should be better. So it's something that should be available in the next 5 to 10 years for user for the need like yours.
Oh, very good. Good to hear. Thanks.
Yes, that's Thank you so much. That's the kind of speed dating I told you about. So
Yeah.
you will have many emails now answering to your requests. And I have a company here that is a little bit of the Alibaba cave of all what you need. We have Key from OptoSigma. Can you unmute? Can you tell us a little about OptoSigma?
Yes, I thank you very much for inviting me today. We have one slide. I have been told that I have only one slide to show, and only one slide to show. A company has over 45 years of experience and in manufacturing laser photonics component. I don't know if everyone's seeing my slides.
Yeah.
Okay. So OptoSigma, in some word, we optics and optomechanics manufacturing back in Japan, and photonics components talks to us, and so we also building systems. This is one of the core competency of OptoSigma is not only manufacturing components, but we also gather in different area of the world that able to offer to research, life science and semiconductors and any few applications of component and systems. So the system that we build are not only for integrating into machine, but also in your labs and OEM. So just a few words, and I just be really interested, really attracted by the talks of Mr. Popp and also Federico from ELI. I think we have solution for you on the topics of the microscope system that you looking for a partner, and also custom optics solutions for Federico at ELI, that we have been supplying a lot of mirrors, transport mirrors in Czech Republic. Yes, thank you very much. That's all.
Thank you so much for the nice summary. So Just, do you have another question or?
No, thank you very much. I'm hoping for much replies.
Yes, and we will keep in touch because you have to be there for hyperspectral 3D sensing. We have so many OTMs that are interesting. And as I said, we will have a dedicated OTM for forensics. So it will be really nice to have you with us again. Thank you so much. So the next talk will be by Kevin from MIT, as I promised. How are you doing, Kevin?
I'm doing well. Thank you very much for inviting me. Good morning and good afternoon to everybody. I'm reporting out here from the New Hampshire office of MIT under COVID. So I wanted to take this opportunity to sort of broaden things up a little bit as well. I'm not going to look at specific technologies, but I'm going to look at more of collaboration with MIT in the areas of photonics and MIT Lincoln Lab. Between universities, we know how to collaborate and we know each other fairly well, researchers are researchers. But I thought, let me talk a little bit about how we can collaborate from company into a university that in areas at which may not be as well known. Again, I'm Kevin Lefebvre. I'm one of the technology licensing officers at MIT, one of 10 that we have. Just to give you some background here. In regards to, a lot of people don't really understand what a technology licensing office does. Well, you can think of us as being the product managers of the intellectual property. We work with the inventors to assess the invention, and then we work with the patent attorneys to try and patent it. We then market that invention out to companies to license it, and then we come up with a license agreement, and then we manage that license agreement through the process at which they're generating revenue. The whole hope here is that it's not only just creating revenue, it's creating a partnership. It's a company that is taking technology, it's coming out of a researcher's lab, the researcher's still doing work in that area, the company still wants to do work in that area, and they continue to collaborate, generate more IP, which then ends up generating more back into the license agreement. We also talk about intellectual property terms when it comes to doing sponsored research, and we manage trademarks and open source licensing. Just a little statistics about our office. We have about 800 inventions annually that come in from our inventors. That's not only from MIT, it's also coming from MIT Lincoln Lab. And I think that, as well as the greater than 150 licenses that we do a year, and we spin out about 30 startups annually out of the office. And I think that's, to me, that's really important. So I come from the industry. I spent 20 years in the industry, but I think this is really important in that I think it sort of breaks that idea that, oh, these universities, they're just doing this high level research, and I'm a company, I've got a problem that that I solve, and universities don't do this sort of research. But we work with companies to generate these spin outs that are companies that are actually going to be developing products. So it's not just high level research coming out of the universities here. So why work with MIT and MIT Lincoln Lab here? And I think we have a unique environment, and it is this combination between MIT and Lincoln Lab. As you can see here by the TRL level graph here, academia mainly works in the TRL level 1, 2, and 3, right? This is knowledge development. This is basic research. However, Lincoln Lab is a funded research organization that is designed to develop and solve problems that the federal government has. So like the two examples I gave just previously, these are actual physical prototype systems that are eventually will be taken and deployed. So it's not just doing basic research, it's also taking that and develop a product. And actually I've got a sort of a good story that sort of outlines this. I sat down with one inventor at one time from Lincoln Lab, and this was for an imaging system that they were flying in an aircraft. And I asked him about the invention. I asked him where he was at in terms of developing it. And his comment was, right now we're going through quality testing. We're doing shake and vibe testing of the system to make sure that it can handle the takeoff and landing and handle being deployed in an aircraft. You typically don't get that in a university environment. University environment, when I turned around and sat down with an inventor and said, hey, I think, I know the VP of this company, I think they would be very interested in this. He looked at his graduate student, the professor did, and said, I think we better start fabricating some of these. So, it's a different mindset. But with that, coming from a company perspective, we're developing and putting a lot of money, millions of dollars into these products already that are ready to be taken and brought into a company and advanced further and to form other relationships. So to give you an example here, and to bring it back to sort of the focus in the photonics. So I manage, the most of the photonics inventions that come out of MIT and MIT Lincoln Labs. I have about 900 inventions that I manage. Think of me as a product manager with 900 products. So, basically I'm pretty busy. About 70% of those are all photonics products. And that ranges everywhere from devices, waveguides, fabrication techniques, PICs, all the way up into system level type devices, right? So an example over here, this is an underwater UAV for doing optical communications. This is a prototype system that was developed to be able to turn around and solve a problem that the federal government had. This down over here in the right-hand corner is a drone with an imaging system on this drone to be able to detect gas leaks. Again, it's more of a prototype system that has already gone through and has done the basic science and has moved it forward. Up on the top here, we're talking about chip level spectroscopy systems. And then as we talked about before in terms of quantum systems, we got quantum network testbed that's being developed and other quantum, first trapped ion quantum chips with integrated photonics. So the sort of the portfolio that's available for the industry to tap into ranges from specific just devices to all the way up to larger systems that can be utilized. So how can we work together here? Well, we can certainly do it by sponsored research, right? You can come in and say, you know, I got some money and I'd like to engage either a faculty member or engage a researcher at Lincoln Lab. In the U.S., we have what we call SBIRs and STTRs. These are government-funded projects, government funding at which you can integrate researchers to do products. Through Lincoln Lab, we have what we call CRADAs. This is Collaborative Research and Development Agreements. This is where essentially you're coming in and saying, hey, this standoff detector that you have developed here, I'd like to operate at a different wavelength. Can you do that? And they would say yes, and turn around and tell you how much it would cost for them to do the research. We have here the Industrial Liaison Program here, and I put the website down here, and that helps you get matching with researchers in terms of what's going on at your company and what's going on at the university. And then we have this Technology Transfer Office, which is where I'm from. You're more than welcome to email me at any point in time. I'd be more than glad to introduce you to some of the inventors that are out there, to be able to turn around and say, this is some of the solutions that they have. See if there's some inventions that are already available to help you advance your product further, and to help create this collaboration. Again, email me at any time. I'd be more than glad to do that.
Thank you very much, Kevin. It is great to have you on our network, and you are the entry point for all the MIT technologies. I just wanted to introduce you to our EPIC network because I'm very happy that MIT is supporting EPIC, and you've been a fan of all the online technology meetings. So let me give again this entry point. Kevin is the entry point for MIT Technology. If you want to contact any of the departments to know what are their Santa Claus Christmas list, he is the right person to contact. Once again, Kevin, thank you very much for this nice introduction to yourself, to this EPIC network, and it's great that you are supporting what we want to achieve. But what we want to achieve is really to get the scientist shopping list. So I'm gonna go now to Fraunhofer CAP. And the reason why I wanna go there is because I really want to hear from David Armstrong how the rest of the community is gonna make Fraunhofer, the great R&D center in Europe, even greater. The floor and the attention of everyone goes to you.
Hello, can you hear me, EPIC?
Yes, loud and clear.
And can you see my slides?
Yes, go full screen and tell us. You should all know that Fraunhofer UK in Scotland is really driving the quantum technologies over there, doing a fantastic job.
Okay, I'll touch on that briefly if I can, Jose. So in the UK, the fireworks come later on this week. I think it's the remember the 5th of November, going back to your introduction there. Anyway, so you may not know, but there's a Fraunhofer in the UK and in Glasgow. Here's the photograph of us in a sunny day. What we do and what we are is we're a research and technology organisation, as you probably know, a UK not-for-profit company, but part of the Fraunhofer network. And what do we do? Well, we develop and make lasers and laser systems, usually for industry, but also with partners in academia. In terms of, it's a little bit like the slide you showed earlier from MIT, you know, what can we do? Well, we can start with, if you like, the photographs you showed earlier, the optical clock system on a bench, the forest of mirrors and optical mounts, and we can take that to a proof of concept system that maybe can be placed in the back of a car and taken somewhere and deployed. But working with partners, we can take that a little bit further. So in this case, this is a product that we developed with Alter Technologies, used to be known as OptoCap in Scotland, and I think Mark Day is on the Zoom room somewhere, but they're very good at packaging, for example, optical devices. So this is a credit card size 780 nanometer source, sub 500 kilohertz. This is the kind of source or device you might use for quantum research, for example. And indeed, we're a big part of the UK quantum landscape, and we're just about to start a £10 million project on the assembly and integration of quantum devices. So it goes back to some of the discussions earlier on small integrated devices, maybe bringing the trapped atoms, the sources, the sensors, and so on into one very small device. That's kind of where we live, is that in between tier level between academic research and commercial devices. In terms of what we can do, well, you probably know in Scotland that there's a real track record of laser research, things like diode pump solid state, we can do that, mid-infrared lasers, OPOs, semiconductor disc lasers, along with our friends at Fraunhofer IEF, and indeed integrated optics using ultra-fast laser inscription of devices into substrates. We also have in our team, guys who are used to designing optics or optical systems for use in defense applications, submarines or tanks. So we can make these devices robust and operating in the field. And indeed, we have electronics guys who are used to making commercial electronics. So we can span a very, very wide wavelength region in terms of devices and sources. Maybe one interesting aspect is quantum research, to give you an idea of the kind of wavelength range required. If you look at the different species that you might want to trap or control as ions or atoms, if you go through, there's lots of different wavelengths. We can't do all of these, but we can participate in some of them. For example, gallium nitride, I know Steve Najda is in the Zoom room, one of our partners at TopGan. So there are semiconductor devices we can use here. Ti-Sapphire we heard about earlier, plus a second harmonic, OPOs, and various gain media, erbium, praseodymium, and so on. Now, we don't claim to do all of these, but we can certainly participate in designing and developing lasers across a very, very wide range of wavelengths. For example, Vasily, my colleague, is on the Zoom room as well. So this is, maybe more laser research, is taking a commercially available pump laser and using diamond crystals to do wavelength conversion to interesting wavelengths for various applications in the yellow and red. And I just inserted this slide just while Just was talking. This is a handheld device. This is more of a system. The laser here was actually made by our friends at Fraunhofer IEF. And this is for sensing explosives or explosive residues. This would be a handheld device. The umbilical you see in the end product, if you like, was not there. So it can give you through, and this is absorption spectroscopy, a good idea of a range of materials, whether it's an explosive residue, a harmful type substance. And we worked with our friends at the German Home Office on this project. This was a European Union project. And finally, I couldn't resist, again, obviously this is almost for fun. The best sensor of explosives is still the dog, who's very good, but we're working on, if you like, gas sensing technologies, very low level, parts per billion sensing using things like maybe laser, acoustic spectroscopy, photoacoustic spectroscopy, for example. So I'll end it there. We're a collaborative organization. We work with industry and also with academic partners to take devices, products to a high level of TRL so they could be deployed. And we don't commercialize ourselves. We hopefully gain some satisfaction from seeing products out there and being used in the field. So thank you very much, Jose and Sana.
Thank you so much, and thank you for joining us today. And can you go back 2 slides, please?
Yeah.
With the guy holding a gun, the one before this one? Yeah. Can you tell us what does it take to industrialize such technique?
Okay. To industrialize, I mean, if you take what we need here actually is a partner willing to if you like, take the final step into a commercial product. If you look at the components in this device, there's a source which is made by IEF, Fraunhofer IEF in Freiburg. So it's a very rapidly scanning mid-infrared wavelength source. There is a sensor from Vigo in Poland, and we did the optics and the integration here. Essentially, it's looking at laser absorption spectroscopy at a distance in standoff. So it requires a number of partners. This was a European Union project. A number of partners who can provide the source, the sensing, the optics, some software as well. And what it probably needs in the future is, you know, an integrator to take it to a different level, and someone willing to commercialize the system.
Thank you so much. Thank you for being open to collaborations as well. I would like to see first if we have any questions in the room. And I really hope my friend Mercia from Vixelum is here. I really hope he can unmute himself. For Vixelum is an amazing photonic solution provider. And all right. So do you have any questions? Yeah.
For me, this is fantastic slide when you show us the market demand that we have for wavelengths in exotic range, and we are looking at the 532 nanometer as one of these golden wavelengths. Are you looking for cooperation on this, basically on the laser or on the optics? Is there any Santa Claus Christmas list? Because we have the best components in Epic Network to actually supply these particular challenges.
Yeah, well, my colleague Vasily is on the line as well, but I think the Christmas list, you know, similar to some of the requirements earlier, is high quality optics that operate at appropriate wavelengths in terms of damage, transmission, reflection, and so on and so forth. Optical assembly, high level optical assembly. I mean, we work on systems for space also, for example, so resistance to vibration and so on. On this particular piece of work, you know, we're open to collaboration. So if someone's sitting there thinking, I could do with a 573 nanometer source for ophthalmology or what have you, then we are happy to listen to people.
And once again, I would like to congratulate you on the amazing work that you're doing, working with Thales UK and bringing these cost imaging technologies to the market for quantum technologies out of this world. I would like to just dedicate 3 hours of my life to make a meeting just for that, because it's a paradigm shift on quantum technologies in Europe. Once again, congratulations. Thank you very much. Back to Sana-Pyka.
Yeah, thank you so much, Jose. And if we don't have another question, I'll be really happy now to hear from Nathalie Piquet. Nathalie Piquet is a very famous name in the quantum world. We're very, very lucky to have her today with us from the Max-Planck Institute of Quantum Optics. How are you doing, Nathalie?
Yeah, good. Thank you very much for the kind introduction. Can you see my screen?
Yes, you can start now.
Yeah, so then I'm starting now. So yeah, I'm from the Max-Planck Institute of Quantum Optics, and I want to give a quick overview of some of the topics that are motivating us in my group. And especially we try to develop new approaches to interferometry and to spectroscopy using laser frequency combs. So I'm not going to give a scientific talk, but I can just explain what is a frequency comb. A frequency comb is a spectrum which spans a very broad spectral region and which is made of narrow, evenly spaced laser lines. And the spacing between these laser lines is what we call the comb line spacing or the repetition frequency. So most of the time, frequency combs are based on mod-lock laser, and in such case, the comb line spacing is the repetition frequency of the pulses in the mod-lock laser. And probably some of you have heard about frequency comb and know that they are a tool which is now widely spread for frequency metrology. They have revolutionized this field. But in my group, we are exploring new applications of frequency combs. That's what we have done over the past 15 years. And one of these applications are dealing with interferometry with frequency combs. And so in the lower graph, you see a typical setup of what we have. We take 2 frequency combs and we try to make an interferometer out of them. So in practice, in what is explained here, we have 2 frequency combs which are of slightly different repetition frequency. So the period of the pulses is slightly different. That's a setup for spectroscopy. So one of the combs interacts with an absorption cell. Then we combine the 2 combs on a beam splitter and they beat on a fast photodetector. And because the 2 combs have slightly different pulse repetition frequencies, everything is as if the pulses from one comb were walking through the pulses from the other comb. So in doing this, we mimic a scanning Michelson interferometer. And with a setup like this one, all what one can do with a Michelson interferometer, we can do it with 2 frequency combs. So there are more evolved setups which involve more frequency combs, but simply with these two frequency combs, by replacing the Michelson interferometer, we can think about Fourier transform spectroscopy, about ranging, distance measurement, about optical coherence tomography. So there are really many applications, but not only we replace the Michelson interferometer, but we outperform it. First, because there are no moving parts. We also don't have the geometric limitation of the Michelson interferometer, so no wavefront distortions due to the moving parts. We benefit from the frequency comb calibration. And with all this, we still keep all the advantages of the Michelson interferometer. And so, for instance, as a Fourier transform spectrometer, we can measure over a broad spectral span with a single photodetector. And so that this type of activities towards developing interferometers involving frequency comb, which have kept us busy over the past decade. And what is specific in our approach is that we develop everything, starting from the comb source up to doing the science, which motivates our instrumental development. And so in the next two slides, I give an overview of what we are doing. And so it starts with the development of the frequency comb sources. So essentially the frequency comb sources which are suited to our experiment are not commercially available or not entirely commercially available. So our work is to develop the sources which are suited. So sometimes we assemble commercially available parts. For instance, we will buy a laser crystal and buy some mirrors and make the laser ourselves. Sometimes the laser is available, but it is not emitting in the right spectral region, so we need to frequency convert. And sometimes we also do this work in collaboration with other research groups, especially when it involves nanophotonics. Essentially, we have a very broad range of subjects of interest, which are quickly summarized here with the main goals. We want different spectral regions, a different type of stability, different comb line spacings. In some experiments, we want to change the comb line spacing within the experiment. In other experiments, if it is fixed, we are happy. For some setup, it doesn't matter so much that the setup is bulky. It can be a laboratory setup. For other experiments, we would like to have everything on a single chip. And so we are really eager to find new commercial solutions which are based on a new type of lasers, but new photonic solutions. And we have already explored many of these solutions, which are quickly listed here. But we follow very closely all the progress in ultra-short pulse laser and frequency comb technology. And actually, when we are at this point where we have our new comb source, the work continues, or the work starts, because we need to assemble the spectrometer, the interferometer. And so it means that we have also our expertise, which is dealing with developing the instrumentation for using the comb sources. So it means developing an interferometer, developing measurement techniques for ranging or for spectroscopy with some particular modalities, like we can be in very low light solutions. We develop also some sampling techniques for the spectroscopy. Well, one obvious technique is absorption spectroscopy, but of course, as the frequency comb have ultra short pulses, we may also want to do nonlinear spectroscopy over broad spectral bandwidth. And we may want to have instruments which combine several diagnostics. And finally, in our work, we are always motivated by the application. We never develop an instrument without having a scientific problem in mind. And in my group, we are more dealing with fundamental motivations. So essentially fundamental spectroscopy, precision spectroscopy of atoms and small molecules, or distance metrology. But we have also many collaborators that we help in building their own experiment. And these collaborators are more motivated towards applied spectroscopy, for instance, for trace gas detection or for biology. And so here also we use really a lot of commercial products, which go from the very basic optical components to already assembled cells, detectors, ways of sampling a time domain signal. So that's, I think, a rather interdisciplinary field. And I think I am done with this quick overview, and I'm happy to have some questions.
Thank you very much for a great presentation. Thank you for looking for the partners in photonics that can help Max-Planck being one of the leaders in the quantum optics in the world right now. When you're talking about, because that was a fantastic thing, you showed us the frequency comb laser setup, and then you showed us how the chip will look like, and you said that you're already working or looking for collaborations on this sector. For me, this is something that is when I get goosebumps when I see things like this. Are you working with companies doing photonic ICs? Is there any particular challenge for companies that are developing this technology that could help you with? Because all of them are members of EPIC and will be more than happy to introduce you.
Yeah, well, we are always looking for new frequency comb sources. Most of the femtosecond lasers which are commercially available are not stable enough. So really low noise sources are interesting. At the moment, we have good solutions in the near infrared and in the mid infrared. We are looking towards the UV component, so UV, either UV laser systems or optics or detectors is still a challenge. And we want to go more and more towards the UV. So at the moment, we are in the very near UV, let's say 350 nanometers. But our question is, how far can we go in the UV? And we are, of course, dreaming of XUV or perhaps even soft X-ray or whatever in a decade or so.
Thank you so much. This is very nice to know, and there will be a lot of introductions coming your way. But I have my friend from Optical who wants to say a word.
Hi.
Yeah.
Hi. Yes, I'm sure that Natalie is already in contact to our experts on frequency combs, and I'm sure she knows about our frequency combs. I mean, it's more like standard solutions. So I personally, I am interested in dual comb spectroscopy, and we do have some people that are interesting. We have some inquiries lately, and tricomb spectroscopy is also a big new subject. So I think it's a very interesting new field for us. I would be interested in more details on what you're expecting from your either a source to build your own frequency comb, or maybe even a ready industrial solution, if that's also an option.
Yeah, so in the past we have, in the beginning we have really tried a lot of possible suppliers, because what we can buy, we always prefer to buy it because we save a lot of time. And it turned out that, well, there are some building blocks which are available, but you don't have essentially this experiments where you interfere two combs together require a huge mutual coherence between the two combs, and this is something that you don't find commercially available. So there is still always a step, and so depending on the supplier, there are femtosecond lasers which are not suited at all. Because they are much too noisy, whereas there are lasers which are suited but still require a significant input from the scientist. And it's sure, so I understand that there is not the market, or not the market yet, for the companies to really develop the dual comb systems that would be turnkey. But it's sure that, to my knowledge, at the moment, it doesn't exist.
I think, Sita, you have to talk in private with them in the one-on-one meetings. I have one more person I want you to talk to, Darius from Fluence.
Hi, thank you very much. A quick question, not to make it too long, because I very much like frequency combs because of my past experience. So what do you think is the best repetition rate, or the future repetition rate where these frequency combs are going? Because I observed that maybe it's going towards gigahertz nowadays, and it's like some hot topic a little bit. But is it actually useful, in your opinion? Is it something you would like to have?
Yeah, if you think of spectroscopy applications, it essentially depends on what type of spectroscopy you want to do. The frequency combs which are currently available, they typically have a repetition frequency of the order of a few hundreds of megahertz, which is good for interrogating gas phase transitions, which are pressure Broden or Doppler Broden. So what you can do works, but that's not revolutionary. And so for me, the needs are really either towards very low repetition frequency, where you can go for very high precision spectroscopy, or very high repetition frequency, where you could go for, so high repetition frequency would be more than 50 gigahertz, hundreds of gigahertz, where you could go for spectroscopy of biological sample, spectroscopy of chemistry relevant in very short times. So I think there is really a huge
room for cooperation.
Possibilities for new type of repetition frequencies.
This was your first ever EPIC meeting. I think you enjoyed it. Please keep coming because Max-Planck is leading the quantum optics research, and we want you to be more involved with EPIC. Thank you so much for a great presentation. It's been a great meeting. We talked about 6 different application fields. We had the medical R&D and Leibniz. Professor Popp was looking for clinical validation, regulatories, and CE partnerships. We had metrology, and PTV gave a great presentation. And they have a challenge, 313 and 323 nanometer lasers and detectors. Great presentation from ELI. It was an honor to have you here. And they were talking about especially the optics, high laser-induced damage threshold. We had the best IBS coatings in the world here in EPIC, so I'm very happy that we're going to provide you with a lot of options. Forensics was a key market, and the Dutch National Police Agency, oh my God, the Dutch National Police Agency was here telling us about different needs on 3D imaging, footprints and tool marks. They also had a problem with the identification of gunpowder, and it was proposed Raman spectroscopy by Professor Juergen Popp. And we also did want to look at specific metal detection inside humans. He also said inside a dog who ate the kids, but mostly inside vehicles. The diamond Raman laser that Fraunhofer Juergen presented had a key challenge. We need high quality optics and lasers for 532, 573 and 620 nanometers. And finally, Max-Planck, they want to integrate further their frequency comms, and for that they need integration technologies and low noise femtosecond laser. What a fantastic meeting today. Thank you so much for making my dream come true, of making all these online meetings and find ways for people to cooperate. You have to keep cooperating, you have to keep coming to these meetings. Just remember, the EPIC staff is here to help you. All we want to do is to make sure that you are getting introduced to the companies. If you want to get in touch with any of the participants, all you have to do is send me an email, jose.pozo@epic-asom.com, and I will be more than happy to make the introduction. On behalf of a super EPIC team of people who love introducing companies, of people who love photonics, I would like to say that please keep a look at all the upcoming events, and please register and show up and participate and be introduced to the potential partners, customers and suppliers. If you have any questions about medical technologies, about integrated photonics, about laser technologies, about quantum optics, we have EPIC dedicated staff to support you on that and to find with you the best way that the leading and biggest photonic association in the world can help you. Until the next time, thank you very much. Goodbye.